Hello, who do we have here? Welcome. Thank you for joining us, and sorry for the slight delay. Had a slight technical glitch. I see that's Tabiso. How are you, Tabiso?
Oh, hello, sir. Can you hear me?
Yes, I can hear you.
Yes, I'm doing okay, sir. I'm doing okay.
Okay, that's fine. Thank you. So we'll be starting shortly. I'm just gonna share my screen and finish up with the setup. Then we can go on to today's business.
Okay, no problem.
Sharp. Right, can you see the screen I'm sharing already? Okay, so I've set the recording for the benefit of those that are not able to join us at the moment, so that they can be able to follow up on the proceedings at their own time.
Okay, yes, sir. I can see the screen now.
Perfect, thank you. Okay, so I think everything is set. I'm just gonna start. Welcome for you guys on Teams and guys that will be joining us from YouTube. I'm sure on YouTube you can also hear or receive the audio feed perfectly. Okay, so today we'll be covering Gauss law. You have covered questions number 25, I think, from question number 24 to 33. Those questions on Gauss law have already been covered. So if you missed anything there, you can revisit the recordings either on the Teams recording, or you go to the Yellow Physics YouTube channel. You'll find the stuff recorded there under the videos. So yeah, I'm sure we can proceed with that section on Gauss law, which I'm sure one of you can just give us a brief on what Gauss law states. Then we can pick it up from there. So welcome Lisa Kanya and Zenande. You are also welcome. I see you've joined us, and thank you for taking your time to join the platform. So my simple question is, Gauss law, what does it state? What does Gauss law say, or what is it about in your own words or in your own understanding of Gauss law? Just give us what you think. What is it about? What does it concern? Feel free. This is not an exam where you would be afraid to give the wrong answer, but it will be good for practice so that you'll be able to get to the exam with the correct answers. So just give me what you think you have picked from what you've learned on Gauss law so far, and that will help us continue. So you don't need to say it word for word as it is given in the textbook. You can just tell us or just comment on it in terms of what it refers to or what it relates. Then I'm sure that will be a good starting point. Anyone, guys? So in one of our previous sections, we talked of flux, electric flux, phi. I can call it phi E, the electric flux. And I defined this as the number of electric field lines because it is what determines what we call the electric field strength, which you have known as E, right? So I can say it's proportional to E, and basically phi E, this electric flux is equal to E E dot A. E dot A. So you have learned or come to learn that area is basically a scalar, of which it is. But for this particular application, the area that we consider is the area perpendicular to the electric field itself. So we have a unit vector that is pointing in the direction perpendicular to the area, which gives this area vector. So this area vector is that magnitude of the area with a direction pointing perpendicularly to the direction of the electric field. So we consider that as an area vector. So with that in mind, it makes this what you call a dot product or a scalar product, where we have magnitude of E multiplied by magnitude of that area times cos theta. So the angle of the directions between the electric field and the area vector normal to the area itself will be the theta that we consider for this calculation of flux. So that would lead you to an understanding of this electric field, which we know as a vector, to say the electric field is what we call the electric flux density. It's E over A perpendicular to the electric field. So it is the flux per unit area, number of electric field lines per unit area. So now Gauss law helps us to calculate or to find this electric field for any given surface. So from Gauss law, we have come to define a surface that we refer to as a Gaussian surface. So on a Gaussian surface, basically a Gaussian surface is I can say, yeah, an equilibrium surface. It's the surface where we have got the electric field if I could say, yeah, the electric field, or it could be the potential, it's an equipotential surface anyway. So the potential along that surface becomes like in this case an equipotential surface. So our Gaussian surface would simply enclose a region. So it is that surface that we can put to enclose a region, but it can take any form or any shape. We can just define our Gaussian surface like that. But now for the electric field is defined whenever we have charge. So if we have charge within such a surface, the charge can either be at that point, or it can lie at any other point, or otherwise there. So no matter what the position of this charge, if that charge is at position 1 or 2 or 3, and it is the only charge that is present inside the sphere, so no matter what its position, this charge will definitely have an electric field that goes outwards, and the number of electric field lines that would emanate from this charge will be the same. The net number of field lines outside of that surface is the same number in total. It is the same number in total. So if that would be a positive charge, then we know those field lines are going out in that direction, right? And hence you have got the same number of field lines. In this case, that's 4, 8, 12. You've got all those that number of all those field lines coming out from the surface. So if you think of it, if we move this charge from that point to anywhere else, let's say there, still we will have the same kind of field. Just stretching out differently. But at the end of the day, it is the same number of electric field lines that are coming out of the whole surface, the surface as a whole. But only the difference is the charge density, or the field strength at this surface at A is greater than that at B. On this side, the field strength on that surface is stronger than at B. But the net field, or the net flux through that surface, is the same. It is due to the charge. So now this leads to Gauss law, which says that the electric field through a surface is directly proportional to the electric flux phi E. The electric flux through a surface is directly proportional to the charge enclosed. And this gives us that equation. If we put the constant of proportionality, which is the epsilon, free space permittivity, we've got that expression. This is basically what Gauss law simply says. So if we have more charges in there, the number of field lines increases, the net flux through that surface also increases. Okay, that's it in brief. So we've said this is independent of shape. So if we have the same charges on this kind of shape, then we have the same number of field lines. It actually all goes like that. Whether shape or volume, you increase the volume, still the same number of field lines. So it's independent of all that. It's only dependent on the enclosed charge. It's only dependent on your enclosed charge. Okay, that's it for my introduction. I'll leave that story there so that we can start with today's business. So on question number, was supposed to start at number 34, I think, 34. So if you have questions, guys, please feel free to just speak out. Just speak out. Do not continue keeping quiet. Or you can just write something on the chat section. I'll be able to see your questions via the chat. So the question goes, a long non-conducting cylinder of radius 6 millimeters has a non-uniform volume charge density given by rho equals to alpha r squared, where alpha is 6.2 microcoulombs per meter to the power 5, and r is the distance from the axis of the cylinder. So this is a non-uniform system, and the way in which the density of the charge of that cylindrical non-conducting cylindrical block or material is given by that expression alpha r squared. So it varies as a function of the square of the radius. So now, what is the magnitude of the electric field at a point 2 millimeters from the axis? So a hint is given there. Q enclosed is equal to the integral from 0 to 2 millimeters, where we need to find the electric field of rho dV, of the charge density times the change in volume as our integration operator there. So we need to find the electric field at 2 millimeters. So where do we start? We already have the given quantities. So the given data tells us that we have rho, which is alpha r squared. What else do we have? The radius r being equal to 6.0 times 10 to the minus 3. I've changed millimeters to meters already. Alpha itself, which is the constant there, is 6.2 times 10 to the minus 3 coulombs per meter to the 5. And we want to find the electric field at a point r equals to 2 millimeters. So we have our measuring point along r, which is we can use capital R there to measure the point where we are concerned with the electric field, and this is 2 times 10 to the minus 3 meters, 2 millimeters, and we need to find the electric field. This is the unknown. So that's the all the data given in that question. And most importantly, the hint Q enclosed is said to be equal to the integral from 0 to 2 millimeters of rho dV, like that. So one thing, we have definitely to integrate something like this to find the total charge enclosed by that Gaussian surface, which is a radius 2 millimeters. Remember, the radius of this whole cylinder is 6 millimeters. It is 6 millimeters. So we could find the total charge of the whole cylinder. Yes. Sorry about that. Okay. So we'll need to integrate the enclosed charge enclosed over the given radius from 0 to 2 with the function alpha rho squared dV. Then we need to also relate E to Q. So we need to relate E to Q. So there we are. This is the expression, these two expressions here. So this one in black and this one in red. So already our phi is Q enclosed over E naught. It means therefore if we combine the two, our E equals to Q enclosed over E naught divided by the area. So therefore E equals to phi E, we replace with phi E with Q enclosed over epsilon naught, then over the area. So this is the expression for the electric field that we would have to resort to get the electric field that we need. to find the magnitude of the electric field. So besides that, so I can put that expression there. E equals to Q enclosed over epsilon naught divided by the area. This is the surface area of the cylinder. So now, which means our goal is to find the enclosed charge. So Q enclosed equals to the integral from 0 to 2 millimeters of alpha r squared dV. But what is dV? What is dV? Volume of a cylinder. Is that someone to admit? If you can admit some guys, please do so. For those that will be waiting in the lobby, please, you feel free to also admit them in case I don't see some of these messages. Okay. So are we following so far? Do we follow what we're trying to do with this expression? So our first goal here is to find the enclosed charge, which is the charge enclosed within the Gaussian surface given by the surface area or around the cylinder, this cylindrical charged object, and around that surface area of radius 2 millimeters, we would know what that area is using the geometry, where we know it's pi r, 2 pi r, which is the circumference times L. We get that surface area, which is our Gaussian surface. And then we divide the Q enclosed that we get here by the area. That's the goal. So that's why I'd given in my list of information here, I've given this expression because we need to find E, but we are only given Q. The hint only gives us Q. So we have to evaluate that Q enclosed. E naught is a constant, area is something that we can find. So now where we are here, where we are trying to evaluate this expression, this integral, volume of the sphere can be calculated using pi r squared. Remember your sphere, sorry, now I'm saying a sphere, cylinder. Pi r squared is this area, and L is the length of the cylinder. So you've got area times length, it gives you volume. It gives you volume. So pi r squared becomes that area, and L gives us that volume. So what does that mean? dV dr. dV over dr will therefore be equal to 2 pi r L. So that means dV, therefore, dV is only equal to 2 pi r L dr. So if we cross multiply by dr on both sides, we get our 2 pi r L dr. We use this to change the operator. This is used to change the operator from dV to dr, because remember, we are integrating over a radius. This is the radius upon which the function of the charge density is changing. It's alpha r squared, so it changes as r. So our operator also has to be in terms of r. So what does that mean? 0 to 2 alpha r squared dV would replace with what we found here, 2 pi r, 2 pi r L, 2 pi r L dr, like that. So now we have this function. We can take constants out to simplify the whole thing. 2 pi L alpha, 2 pi L and alpha are constant in this case. Then we integrate from 0 to 2 millimeters. R cubed dr. So this r squared and that r gives us r cubed, and we have 2 pi r alpha outside the integral. So this is a simple integral. What should it give us? What should this integral give us? Anyone? What should the integral give us? Feel free to talk to me, guys. If we evaluate this, what do we get? So integrating would mean we raise the power of 3 by 1. So we have got r to the 3 plus 1, which is r to the 4, and divide by the new power, which is 4. So this is the opposite of what you do when you are differentiating. So this is from 0 to 2 millimeters. So ultimately, this should give us an expression for the enclosed charge, Q enclosed, will be equal to 2 pi L times alpha times 2 millimeters to the power 4, everything over 4, minus the same thing, minus 2 pi L alpha over 4, everything multiplied by 0. So the one that multiplies by 0 is out, we can eliminate, and we express for the enclosed charge. So we have a calculator here. You can also do it from your side. You can also follow up from your side and see what you get, so that we know we get to the same thing. So 2 to the negative 3, everything to the 4. One comma 6, that's 1,6 times 10 to the minus 11. That's for that part, and this and that give us 2. So multiplied by pi L alpha over 2. So this is our enclosed charge. Then what do? We resort to this expression now to get our electric field. So with Q enclosed, which is pi L alpha over 2 multiplied by 1.6 10 to the minus 11 divided by E naught, right? So this is Q over E naught, then everything is over the area. The area we said is 2 pi r 2 pi r. In this case, this area, the area of the surface, remember the surface we're considering is this surface. So it is this circumference, the circumference there, multiply then and with that length there. So that surface, if you open it, you are simply looking at something that is covered by that and this. So it is something like this, making a circumference there, which is given by 2 pi r, and then this length, which is stretching from there to there. So if you spread this sheet, you've got that length and that length. So the 2 pi r is now straight here, 2 pi r, and the length is that one. So this is when you unfold this sheet and make it straight. So if you curve it, you've got your curve making the 2 pi r, 2 pi r, this circumference, and the L is the length. So the area here is 2 pi r multiplied by L. That's the surface area that's making this Gaussian surface. So that means we've got 2 pi r L here, 2 pi r L there. So this is the same. L cancels out. Okay, let me just cancel out using something different. Pi L. What else? Okay, so we remain with 1.6 times 10 to the minus 11 times alpha over 4 E naught R. Okay, something like that. So let's express this. Let's calculate this this part. Your alpha is that 6.2 times 10 to the minus 3. So multiply by 6.2, 10 to the negative 3, and divide by 4 E naught, which is 4 times 8.85. So this is 1.6 times 10 to the negative 11, multiplied by 6.2 times 10 to the negative 3, and then divided by 4 times 8.85, 10 to the negative 12, times 2 millimeters. So if we divide by 4 times 8.85, 10 to the negative 12, we are getting E equals to 1,401 newtons per coulomb. This is the value of the electric field. This is the value of the electric field. I hope you got the same thing. I hope you got the same thing. So remember, we evaluated our Q enclosed in this case by changing the variable. And that gave us an expression for a final expression for Q enclosed here. And from there, applying the limits, we got the value of Q enclosed, pi, L, and alpha. Did we? I don't see an L there. So L was not given, so it didn't matter because that was going to cancel out. But we have got Q enclosed evaluated in terms of that. And now, because we need to find E, we said is given by Q enclosed over E naught epsilon naught A. Q enclosed over epsilon naught times A. This is our expression for the electric field. So now that we have Q enclosed, we know A. We had to evaluate A in terms of 2 pi RL. That's how the L cancelled out. The pi is cancelled out. And the rest of the values that remained are constants or otherwise given values. So with that, we get E equals to 1.4. So of the available options, 5421516, our closest alternative is 1.5. So the closest choice there is 1.5 newtons per coulomb. So some of these differences, it's either a difference of the constants used, especially for your E naught, or the other values, so you would have rounded. But anyway, you have got the order of magnitude being the same, and that will give you C as the best choice. Right, I hope you were able to follow. Yes, there's a question. Please feel free to ask. What's your question?
Say, I cannot see your screen right now.
You cannot see my screen. Let's see what happened. Okay, okay. Thank you for that. Let's see. Okay. Yeah, sorry about that. Something had happened to some section of the screen, but yeah. Anyway, that's how we get to our electric field. That's how we get to the electric field. So in case some part that I was explaining was not showing, I'll just try and rush through this one again. We had to find our enclosed charge from the given hint and do the integration by changing of the variable from dv to dr. And from there, we have an expression for the enclosed charge, which is given here. And from that expression for our enclosed charge, our next step. Am I the only one who doesn't see the screen? Okay, that was Hlaluko. So sorry if I had not read that earlier. Sorry about that. Then with the value of the enclosed charge, we related enclosed charge to the electric field from Gauss' law again, which is an expression that says E is Q enclosed over epsilon naught times A, which is basically flux per unit area. So that's flux density. Electric field is your flux density. So substituting for Q enclosed and everything else is given our area. We've defined our area from that, the area of the surface area of this cylindrical material will generally be the curved area upon which the charge is, upon which the field is coming through. So that surface area is given by 2 pi RL, and dividing by that, we get to our final solution, which is 1.4 newtons per coulomb. So the next question here is number 35. A solid non-conducting sphere we have a solid non-conducting sphere of radius 12 centimeters, which has a uniform charge density, volume charge density again of 30 nanocoulombs per square meter, per cubic meter. Sorry, that's cubic meter, it's volume. Distributed throughout its volume. Determine the magnitude of the electric field 15 centimeters from the center of the sphere. 15 centimeters from the center of the sphere. So R at the point where we want to determine the electric field is at 15 times 10 to the minus 2 meters. Okay, so which means the point is basically outside. If that is 12, that point is 3 centimeters from the surface. That's our point P, where we need to find the electric field. We need to find the electric field at P. So what do we do with this one this time? What do we do with this question? So one important thing with this information given here, this one is we can talk of solid spheres, hollow spheres, solid conducting, solid non-conducting, hollow conducting, hollow non-conducting sphere. All that information, it tells you something about the distribution. It is very important. It is very important. So if the case with the hollow, whether it's a hollow conducting or non-conducting, one important thing there to note is you don't have an electric field inside a hollow sphere, be it conducting or non-conducting. So if it is a sphere, remember a sphere is not a circle, a sphere is 3D. So in that sphere, you are looking at something like a ball. And if the material of that hollow sphere is either a conducting material or non-conducting, and it's charged, then there is no electric field that would simply be found within that hollow sphere. So for both conducting and non-conducting. Point number 2, if the sphere is solid and non-conducting, or it's an insulating sphere, so non-conducting and insulating, one and the same thing, insulating solid sphere, then the charge is distributed uniformly throughout the material from the center. So if it is there's an even distribution of charge like in this question, then the charge is spread from the center outwards uniformly. So we have charges distributed throughout that non-conducting sphere material, different from a solid conducting sphere. In a solid conducting sphere, the charge is basically mainly distributed on the surface. So a solid conducting sphere will have its charge on the surface, and as a result, it doesn't have an electric field inside the sphere again. So you should take note. That information, I think, will be important for you to remember each time you are looking at a question. So here we have a non-conducting sphere. We know our charge is distributed from the center. And so as we go outwards, the charge is increasing. The electric field does exist in a solid non-conducting sphere. We do have an electric field which is non-zero. So there's an electric field and it increases linearly as the radius. So the electric field would increase in there. Then it begins to decrease as the inverse distance law. So it decreases as E equals to KEQ over R squared, inverse square law again. So it decreases inversely as the square of the distance to the point of measurement. So in this case, it is important when you are given a question to first think or first ascertain whether you are still within the radius of the sphere or you are outside, because the expressions for those two areas or those two regions are very different. So this one is a simple case. We have R being equal to, the point of measurement is 15 centimeters, which is greater than 12 centimeters, the radius of the sphere. So we are outside. Our measurement will therefore mean we'll have to find the charge and use this expression. We need to find the total charge for this system. So since we're given charge density, Q is equal to, let me use charge density, this is rho is equal to Q over volume. So this is, so it means therefore Q equals to rho, the density, times the volume, which is 30 times 10 to the negative 9 coulombs per cubic meter, multiplied by the volume, which is times 4 over 3 pi, R is 12 times 10 to the minus 2 cubed, pi R cubed. Pi R cubed, this is the volume. So that will give us the total charge of this system, the total charge of this sphere. Can someone calculate that for us? Four over 3 multiplied by pi multiplied by 12 times 10 to the minus 2. Everything cubed. So that's 4 over 3 pi r cubed. That's the volume. And multiply this by 30 nanocoulombs.
It's 2.1.
You have your 2.17 times 10 to the minus 10 coulombs. This is the total charge of the sphere. This is the total charge on the sphere. And with this charge, we now apply to the expression for the electric field. E equals to Ke Q over R squared, which is 9 times 10 to the 9 multiplied by 2.17 times 10 to the negative 10 all over 0.15 squared.
$86.8.
What's that? I think I had something like an answer. $86.8. Ah, that's what I had in the whisper. 86.8. What happened to your voice?
My voice has problems, sir.
Okay, that's fine, but I'm sure you got the correct answer. 86.8 is 87 rounded to two significant figures. So that's D. So that's how we get the electric field at 15 centimeters from this non-conducting sphere. So by using this expression, what assumption are we making? What assumption are we making? Remember, the radius of the sphere is 12 centimeters, right? And the distance, we don't consider the distance to the point of measurement of the electric field, which is 15 centimeters, to be 15 minus 12, which is 3. Why? Because we assume, or the system behaves, or the electric field would behave as if all the charge were concentrated at the center of the sphere. It will behave as if all the charge were concentrated at the center of the sphere. So we would consider also the radius as 15 to the point of measurement of the electric field. Okay, I think so far so good. Question number 36. I think this one you should help us answer. It relates to a lot of things that I've just described. A positive point charge, Q, which you can see as a tiny blue dot there, is placed off center inside an uncharged metal sphere. So this is our metal sphere with the inner surface in red, outer surface in blue. Insulated from the ground as shown. What is the induced charge density, or where is the induced charge density greatest in magnitude, and what is its sign? So where is the greatest induced charge density, and what is its charge? The greatest induced charge density. So the charge density of greatest magnitude is at which point A, B, C, or D? And what is its sign? So the point charge is a positive point charge Q, positive point charge Q. So we have a positive charge Q there. So tell us what you think, guys. What do you think or where do you think will the sphere will have the charge density of greatest magnitude, and what will be its sign? Give us your thought. Oh, something had been written there by Nhlaluko again, 2.1710 to the minus 18. I'm sure that was supposed to be the value of the charge. Yeah. Okay, I don't know why you have minus 13 there. I hope you checked where the error was. Supposed to be 10 to the minus 10. You have a minus 13. Otherwise, maybe you should have maybe you didn't convert something there in terms of the given centimeters. Yeah, probably from the centimeters. Or otherwise it should be something different. I don't know where you could have missed it. Just check where you made the typo. For the value of charge, I got 2.1710 to the minus 13. Okay. Please, I hope you got that one. You corrected that one. Anyway, where do we have the greatest surface charge density? Okay, confirmed. Thank you. Where do we have the greatest surface charge density? Point A, point B, point C, or D? So the reason I had shown this, I talked about this one here, where I said the on the Gaussian surface, the enclosed charge would mean no matter what the position of the charge, you still have the same net charge through the Gaussian surface. But the only difference is the distribution of the field. So it's more intense, closer to the charge. But the question now for this situation or scenario is what will be the charge of that place, the sign, or yeah, what will be the sign of the charge of that place where you have the greatest electric field strength or the greatest charge density, induced charge density. So is it A? Maybe I can ask that way. Just show by raising maybe your hand if you say it's A. Let's see. Okay, good. Those that say it's B, is it B? No one for B. I'll go again. Is it B? Okay, C. Anyone who would choose C here or who thinks C is a good option? What about D? Okay, so 100% all the votes are on A. Everyone that voted for A. So A is the correct answer. The greatest surface charge density induced there will be at A. What will be the sign? What will be the sign? So with sign now, it's a matter of whether positive or negative. So we've already eliminated C, D, and E. That's correct. So what will be the sign, positive or negative? Positive or negative? So remember, we have a positive point charge in there. We have a positive point charge in there. What kind of charge does it induce on the inner surface, which you said is point A? And then the inner surface will ultimately induce again a charge on the outer surface. There's no electric field between the red and the blue line. So that's inside this solid material, there won't be an electric field. So Q in the inner surface will be negative because the positive test charge inside there induces a negative charge on the inner surface. So there'll be a negative charge there. So the overall charge enclosed by the outer surface, which is the blue line, is therefore equal to 0 because you've got positive Q on the point charge, negative Q induced on the red inner surface. So the sum there becomes 0. At the end, there is no electric field around that Gaussian surface from the red line, the inner surface, to the blue line, the outer surface. So the electric field will exist between this point charge and that, because when we draw Gaussian surfaces outwards, we are enclosing a charge, and so there's an electric field there until only the negatively charged inner surface, which is induced with a negative charge. The sum of the two gives us 0, making the charge induced onto the outer surface to be Q again. So if we draw an overall outside Q, our enclosed charge is basically Q, because that blue surface now assumes a positive Q charge, which is the charge of the test charge that's inside this system. So the charge there is negative. The charge there is simply negative. Okay, then now question 37. So please don't allow me to pass if you still think there's something you didn't understand. Don't allow me to pass. Consider a long cylindrical charge distribution of radius r with a uniform charge density. Oh, what's happening with my screen? So which screen were you not seeing? I hope it's not this one. Tell me if you still can't see the screen. Tell me if you can't see, if you still can't see the screen. So our question goes, consider a long cylindrical charge distribution of radius r with a uniform charge density rho. What is the electric field in terms of rho, r, and and E naught at a distance r from the axis when r is less than big R? So we're given this case where the radius there is big R, and this is a cylindrical object like that. So we can have our Gaussian surfaces. We can have a Gaussian surface of radius small r, and it goes like that. So this is small r. So what is the electric field at a distance r from the x-axis? So in other words, how the electric field varies with r inside this system. So we're told that, given information, the charge density, we have rho, that's the charge density, we have r, there's that radius, okay. So we have small r as the any radius from the or any distance from the center of this system, and epsilon naught the free space permittivity. So r, big R, is the actual radius. That's all the information given. So we have E dA is equal to Q over E naught, basically. So EdA will be equal to Q over E naught. This is the enclosed charge. Remember, we said EdA is the flux, so this is from Gauss law. Electric flux is EdA. So the change in the electric flux will be a function of the change in the Gaussian surface area with the electric field strength E. So now, what we have here is ratios of rho, where we know rho is equal to the charge over volume. So this will be Q over 4 over 3 pi r cubed. Let me say pi r cubed like this, where r is the radius, q is the total charge of this cylindrical charge distribution. So the total charge is given by that. And now the enclosed charge, this is generally the expression for the charge density. So the total charge is the big Q. So also the same charge density applies when we have Q enclosed over the volume enclosed, which is basically Q enclosed over 4 over 3 pi, this time r cubed like that. So these two expressions are equal because they are giving the same charge distribution, which is the same charge density rho, and they are just at a function of the enclosed charge and the equivalent or the corresponding radius. So because we want to evaluate our Q enclosed, if we say Q enclosed over the total charge, this will be 4 over 3 pi r cubed over 4 over 3 pi big R cubed. And these like terms can be eliminated, and we only remain with Q enclosed equals to R cubed over big R cubed multiplied by Q. So back to our expression for the electric field, which is what we want to express. We have the flux being equal to E integral of dA. This is a surface integral of this cylindrical object. So what it gives us is that Q enclosed over E naught, and now we evaluate our dA is the same that we used at some point when we opened up the surface area of the cylindrical object. So the area there is 2 pi RL. So integrating over that surface gives us 2 pi RL equals to the Q enclosed is R cubed over big R cubed multiplied by Q divided by everything over E naught. So we can now evaluate the electric field by dividing by 2 pi RL. Both sides. Then that gives us E equals to this and that. We've got squared. So that's Q times R squared Q R squared over 2 pi R cubed E naught R cubed. Did I do it right? Q r squared over 2 pi e naught r cubed. I hope I did that one right, but what we have here, we have rho. So to express this in terms of rho, we go back to rho is q over 4 over 3 pi r cubed. Q over, okay, so we have to express this in terms of rho. So that's q over 2 pi r cubed multiplied by r squared over e naught. So we want this part to be 4 over 3 pi r cubed. So this is the part that we want to express to go back to rho, which is q over 4 pi capital R cubed. So we multiply by 4 over 3 there, and at the top and at the bottom. So this becomes 4 over 3 q. Okay. 4 over 3 q over 4 over 3 pi r cubed, and we have a 2 there. So this 2 is still there. This is now our expression for the rho. So we're just evaluating this so that we have got rho in that expression. And the rest of the part remains the same, r squared over e naught. So this is 2 over 3. So the 2 cancels, 2 into there is 2. So we've got 2r squared over 3 with the rho there, e naught. Don't know if there's something close to that within the answers given. Nothing with a 3. So 2r squared is pi r squared there. The pi is still there. We don't have pi. We've got r squared and rho. Rho times r over 2 e naught. Okay. So we'll just do some testing to see where I could have put the wrong expression before we jump into some serious conclusion. Okay, so we will start again. I'll just go over this again in case I made an error to make this expression. Our electric flux, the flux is EDA, that's correct, which is Q enclosed over E naught, that's also correct. The charge density is charge per unit volume, the volume being 4 over 3 pi r cubed. And that's charge enclosed over volume enclosed will be charge enclosed over 4 over 3 pi r cubed. And the two expressions being the same, it means that's r cubed big small over r cubed big times q. This part is okay. Then comes this part, the surface integral. Consider a long cylindrical charge distribution of radius r. Okay. Yeah, I think this was correct. So what is the electric field at a distance r from the axis? So we expressed our Q enclosed as r cubed small over r cubed b times q divided by epsilon naught, which is okay. And the surface area there is for a cylinder 2 pi r. So r in this case is the radius, of our Gaussian surface. R is the radius of the Gaussian surface upon which we are integrating to find this electric field. So that is okay. Multiplied by L. And now dividing, I think that's a need to be more careful. We eliminated R to remain with R squared. Then this was R squared over R cubed multiplied by Q. R squared multiplied by Q divided by R cubed multiplied by 2 pi E naught L. There's an L there. What happened to this L? Okay. I see an L. I left this L, 2 pi E naught. Actually see this L here. Multiplied by R cubed. So I have to return that one there. Then expressing this in terms of the density. It has to be Q over 4 pi E naught R cubed. 4 pi R cubed without the E naught, Q over 4 pi R cubed. So it's multiplying by 2 over 3 on both. Yeah, multiplying by 2 over 3. I think this is somewhat correct. So I'll just change this part. If we multiply by 2 over 3 there, and multiply by 2 over 3 there, we've got Q over 4 over 3 pi R cubed, which is our rho. Everything multiplied by 2 over 3. 2 over 3, Q over 4 over 3 pi. Okay. Pi R cubed. Okay, so that will give us 2 over 3 rho multiplied by R squared. There's an L again, which we need there. So that gives us 2 over 3 R squared rho over 3 E naught times L. 3 E naught times L. So this is the expression for the electric field at R. Electric field at R. And nothing close to it here. This is for R less than big R, yeah? For R less than big R. So I think it should give this expression. I think this should be our final expression. So if it is not here, I'll have to cross-check this. I have to cross-check this at least, but if that's the case, then I think in our next tutorial, I'll have to confirm if everything we've done is correct. But I think we've done everything correct according to what I've checked. It means there wouldn't be any of these expressions as solutions if everything is correct according to what we did. Otherwise, if there's an error there, I'll have to highlight to you where we would have gone wrong. Okay. Did you guys identify any point? Did you identify any point I could have missed? I know you guys might have picked something there, which still will be fine, and yeah, it would be great to hear from you. Okay, so for our next question, question number 38. So here we have a large flat horizontal sheet of charge, and this one has a charge per unit area of 9 microcoulombs per square meter. Sorry, what is the magnitude of the electric field just above the middle of the sheet? What is the magnitude of the electric field just above the middle of the sheet. So given the surface charge density, which is Q over area of 9 times 10 to the negative 6 coulombs per square meter, what will be the electric field just above the middle of the sheet? How do we deal with this one? If you would follow the same procedure that we used to find the electric field, what will be this electric field? So how do we find the flux again? Our flux is called EdA, and if we integrate that over the surface, we get that electric flux equals to E times the surface area, and this should be equal to Q over E naught. So for this one, what we are given is we would know the area there is basically length times width, so we can leave that aside. But the relationship for the charge within that area, so sigma equals to Q over A. And for our enclosed charge, that is the Q over the surface area under consideration. Still the same thing, same ratio, uniform charge distribution. So our Q is sigma times A. So in this case, Q enclosed is equal to sigma, which is what we're given, multiplied by the surface area. So we can substitute there. Sigma times the surface area over E naught will give us will be EA. So it simply means if we eliminate these like terms, our electric field is equal to sigma over E naught. So we simply multiply the value of sigma given, so divide the value of sigma given over the permittivity of free space, which is 8.85 times 10 to the minus 12. So this is 9 times 10 to the minus 6 coulombs per square meter over 8.85 times 10 to the minus 12. What do we get? What do we get? I'm getting 1.02 times 10 to the something. I got 1.02 times 10 to the 6, which is 10.2 times 10 to the 5 newtons per coulomb. So that will be A. A will be the answer to this part of the question. Very good. Someone got the same. Tabiso, well done. Okay, then with question 39, another interesting one. Okay, Shalugo proves we got the same thing, so that's great. So with this one, a solid conducting sphere we have a solid conducting sphere, radius 2 centimeters. Has a charge of 8 microcoulombs. A conducting sphere, spherical shell. So it's first a solid conducting sphere with radius that with and charge 8 microcoulombs are what we see here in the diagram. Then we have a conducting spherical shell of inner radius 4 centimeters, which is given by B, and outer radius 5 centimeters given by C. Is concentric with the solid sphere, which means they share the same center. This one is not, the charge is not skewed or positioned closer to one surface than the other. So it is at the center. With the solid sphere, concentric with the solid sphere, and there's a charge of 24 microcoulombs. So that's the charge that is on a conducting shell. What is the magnitude of the net electric field at R equals to 1 centimeter, R equals to 4.5 centimeters, R equals to 10 centimeters from the center of this charge? So R equals to 1 centimeter is inside the conducting sphere. R equals to 4.5 centimeters is between the sphere, not between the sphere, but it's within the inner surface of the spherical shell. So between the inner surface of the spherical shell and the outer surface of the spherical shell, that's the 4.5. So we're starting from the point inside this conducting sphere, the one that is orange, this one, which is radius less than A. 1 centimeter is less than 2 centimeters, the radius, which is the value of A. So we're in there. Then R4.5, you are in the gray area, and R7 centimeters were outside the whole thing. So we want the electric fields at those 3 points. The electric fields at those 3 points. Ideas? Give us ideas. So this is the same diagram redrawn, and we want to find ideally the electric field at a point halfway across the radius, which is that point. That will be our point A. Then, and that point will be our point B, and that point will be our point C. So the first question is, do we have an electric field inside the solid conducting sphere of radius 2 centimeters? Its charge is 8 microcoulombs, yes. But do we have an electric field inside this conducting sphere? do we have an electric field inside that conducting sphere? Before we do anything, do we have an electric field? Lisakanya, Hlaluko, Tabiso, do you think we have an electric field inside that conducting sphere? The brown or orange one, I don't know how your eyes perceive of that color, but it's not important anyway. If you see the colored blob at the center of the diagram, the 8 microcoulomb one, do we have an electric field inside the sphere? What do you think? If you say yes, maybe let's see by a show of hands. Do you say yes? Okay, if you say no, if you think it's no, give us a thumbs up. So it's neither. Okay, there you are. Tabiso, I think that's a no. Yes, there's no electric field in there. You remember what I said about the conducting sphere, solid conducting sphere? There's no electric field inside this sphere. So E should be 0 for this one. Then for B, in B, do we have a, okay, all right, okay, cool. So for B, is it a yes or a no? Do we have an electric field in B? B is that area between the inner and outer surface of the conducting spherical shell again. Do we have an electric field there? So if you say yes, raise your hand. Do we have an electric field within the gray area, or B, as I've shown on this diagram? It's gray area on the question screen. It's the part labeled B on mine. Tabiso says yes. Okay, that's interesting. And the rest? Hlaluko? Lisakanya, what do you say? Do we have an electric field within the between the inner and outer shells of okay, Hlaluko also says yes. Okay, right. Let's see what's happening here. Remember, how do I put this? Redistribution of charge. So we're bringing in a 24 microcoulomb shell around an already charged sphere, which is 8 microcoulombs. So what then happens is the system, basically there's induction anyway. It's what we know as to be induction. So we're going to induce charges first. This 8 microcoulomb, which is positive, induces its charge onto this inner surface, right? So when it does that, remember on the outer shell that we're saying is supposed to be metal conducting, right? So conducting associated usually with metal, but that's conducting anyway. So if it's conducting, the 24 microcoulombs is concentrated or is distributed around the surface. The 24 is distributed around the surface, so it's basically positive. So I'll just put that to just show the distribution. So we have the 24 microcoulombs distributed around along the surface, along and around the surface like that, and the inner surface containing nothing initially. Now, because of the induction from these 8 microcoulombs, the 8 microcoulombs, what does it do? It induces a negative charge, a negative 8 microcoulombs on the inner surface. So we've got a negative 8 microcoulombs there, such that in this region. So if we're enclosing, if we look at the field will exist between this central charge and the inner surface of this sphere, right? So the field will actually occur or be induced between this inner circle, this inner sphere, and the inner part of the shell. So it induces a -8. So this will be overall -8 microcoulombs. And these charges will leave an extra +8 microcoulombs on the outer surface. So which means we have negative charges being drawn to the inner surface to give a -8 charge, leaving this one with an overall of 32 microcoulombs. What is this 32 now, which is on the surface? It is a sum of the initial 24 and the 8 that was in there. So now if we draw a Gaussian surface around the sphere, first sphere inner, we'll find there's an electric field. That electric field is just moving from that surface to outwards, from that surface and outwards. Where are the other nicer colors? Okay, I'll take that one. Okay, that's fine. So on this diagram, that means we have a field that will be out in that direction, like that. And therefore, if we draw a Gaussian surface, we'll actually find there's a flux or at least charge enclosed. When we go out from the inner surface into this black shaded part, which is the material within the spherical shell now, the total charge is 8 microcoulombs minus 8 microcoulombs is 0. That would mean the electric field inside there is also 0 because you are not enclosing any net charge. So there's no field in there. There is absolutely no field in there. But at that point at C, the electric field is KE, Q, which is 32 microcoulombs, over the radius, which is 7, what is that, 7 centimeters squared. 7 times 10 to the minus 2, or 0.07 squared. That is how we find the electric field at C. So you can evaluate E at C and C. Let's see what you get. Let's see what options we have there. 0, 0 and 58.7, 0, 0 and 7.99. So E is out because the initial two electric fields shouldn't be non-zero. They should be 0. So our answers are between A and C. Our answers are between A and C. So what do you have? What did you get? What did you get? What do you get? Is it A or it's C? We have reduced the options to those two. Is it A or it's C? So I'm getting 58.7 mega newtons per coulomb times 10 to the 6 newtons per coulomb. That's the electric field at C. I hope you guys also got the same thing. And if you have any question, please feel free, you guys you can ask. Now the final question for the day. A solid insulating sphere of radius A has a uniform charge density throughout its volume and total charge Q. Concentric with this sphere is an uncharged conducting hollow sphere. Okay, so it's still conducting, whose inner and outer radii are B and C as shown in the figure in question 39. So same as this figure here. We have a solid insulating sphere, so this time it's a insulating sphere inside there. And total charge Q, then the conducting hollow sphere encloses it with B and C as its inner and outer ready together. So Tlalugo got A, that's correct. Thank you for that confirmation. Really appreciate. So B and C are the inner and outer ready of the inner and outer surfaces. And K, it says concentric with this sphere is an uncharged. In terms of Ke, R, and Q, the magnitude of the net electric field at R less than A, R between A and B, and R between B and C respectively is, so the value of Ke is that. So what will be the magnitude of the electric field at R less than A, R between A and B, and R between B and C? So less than A is within this sphere. The conducting, non-conducting sphere, I think it's non-conducting. It's insulating, yes. So inside that insulating sphere, what is the expression for your electric field? R less than A. Then the next part, R between A and B, which is in this region. How would the electric field vary? And when R is greater than B and less than C in that region, how will the electric field also vary? So that's the question, and how do we answer that? So EA, still EA. This time, this is not a solid. Remember the difference I've highlighted there. This initially was a solid conducting sphere inside. So now we've got a non-conducting sphere inside. The whole story changes. So how does it change? The electric field there will be proportional to, did we even get to, okay, so with this, it's basically the same expression that we have here. So in this case, we are saying we are looking at how R varies, and the electric field varies as a function of R. So if you take, for example, this very expression here, or this was anyway, we used this one for this one was for the conducting cylindrical material. So if we have a sphere anyway, we use the same approach to find our Q enclosed, and we have our Q being given by a ratio of the. Oh, now I see. This formula is wrong. This formula is supposed to be volume there is pi r squared L. This is volume of a sphere. Was supposed to use volume of a cylinder there. Sorry guys, now I see. Now it makes sense. So it was that part, I'll come back to it. But anyway, at this point, if we are within the sphere of a radius A, then we have the same thing, our Q enclosed over Q is equal to R cubed over a big R cubed. So that means Q enclosed is therefore equal to R cubed over big R cubed times Q. Then we can express our electric field E times A equals to Q enclosed over E naught. So if we are inside when R is less than A, where A is like the big R, the radius, then E multiplied by 4 over 3 pi R cubed is equal to Q enclosed, which is R cubed over big R cubed multiplied by Q divided by E naught. Now, this is not volume, this is 4 pi R squared. This is 4 pi R squared. Surface area of a sphere. So E will therefore be equal to, when we divide by 4 pi R squared both sides, we get E equals to, this R squared cancels the 3 to leave a 1 there. So we've got R over R cubed multiplied by Q over 4 pi E naught. So this gives us Q over 4 pi E naught R cubed multiplied by R. So remember, this R, this one that I'm using as capital R is basically the A. It is that radius given as A there. So this A is constant, 4 pi E naught constant, Q is the total charge of this system. So the electric field is proportional to the radius. The electric field increases as the radius. So when we are inside this, in the inner part, so I'll draw electric field versus radius and E. So for this case, when we are inside up to A, so this is A, then this is termed B, and that point is C, and this is just R extending like that. So up to A, the electric field increases proportionally to R. Then outside, it decreases exponentially. Then between B and C, it's 0. And from C onwards, the electric field is coming from a point where it also starts from that surface where it's 0 and just starts from somewhere, because the charge there is greater, so it starts from somewhere greater and decreases as a function of R squared, inversely proportional to 1 over R squared. So here it's 0. Here it's inversely proportional to R squared again. So it terminates at that point at B. And that's how this, here it's E proportional to 1 over, is it to 1 over R? No, to R. Proportional to R. E proportional to R. That is the first part of this system. So this is the expression where E is proportional to R for R being less than the radius of the inner sphere. Okay, then the next part, when R is between A and B, E therefore becomes the enclosed charge, Q enclosed over KEQ over R. So this is R less than A, R greater than A, less than B. E will be Q enclosed over R squared. That's the second part. So already this question requires us to express this in terms of KE, R, and Q. So if KE, R, and Q for this one is okay. For this one, this part is the KE, so we have KE, Q, R over A cubed, 4 pi E naught. Yeah, 4 pi E naught. So that's the KE with Q, R, and A cubed. So that one is done as well. And the last part is when R is greater than B and less than C. So it's inside that no man's land where we said there is no way when R is greater than B and less than C, E is always equal to 0. I would take it that way. So the magnitude of the net electric field at that, yeah, so this is a uncharged conducting holosphere. So we have the expression KEQ for the first one, KEQR over A cubed. So this one is correct, A. Then the next one, KEQ over R squared. Because the enclosed charge is basically that charge that's inside. So it's this enclosed charge you can replace with Q there, that's correct. Then the last one is 0. So we have A as our solution. Okay, that's about it, guys. I think that's all. Maybe I'll just have to refer back to this so that we verify the expression. So I'd made an error there to use the wrong, call it the wrong formula. Anyway, it's the wrong formula, yes. So where did we start with this part? I'll just have to go over it to correct. The first part was expressing this over volume, and I don't know why I like the sphere. The volume is not, it's actually pi r squared L. So this should be pi. Let me use a different one so that we see where we're correcting. We have pi r squared L there, and okay. So for this one, the radius is big R. For this one, the radius is small r, pi r squared L. So remember what we have here, we are looking at Gauss law. So the charge density, the volume charge density is charge per unit volume. The volume of this system is given by pi r squared, which is the area, the area of the circle, multiplied by the length of this cylinder. So it will be pi r squared L for the whole system with Q as the charge, or it will be pi r squared, where R is the small radius of the Gaussian surface and the corresponding enclosed charge given like that. So if, because these ratios are giving the same charge density, we can express for Q enclosed by dividing the two. Q enclosed over a Q will therefore be equal to pi r squared L. So there we change pi r squared L divided by pi big R squared L. So with this, the elimination of similar terms, like terms out, will remain with Q as a ratio of R squared over big R squared times Q. So that's one major error that I did on that one. So yeah, that should be overexcitement anyway, but it happens. But anyway, then we come back to this part. We have our surface integral of the area multiplied by E to give for the flux, and this should be equal to Q enclosed over E naught. Our Q enclosed will therefore be R squared, this R squared over big R squared times Q. That's Q enclosed divided by E naught. And our surface area is 2 pi RL. So this one we got it right. It's simply 2 pi RL, and we divide by 2 pi RL on both sides. So if we do that division, we've got E equals to, now let me just rewrite this, R squared Q over R squared E naught times 2 pi RL. Then we cancel that R and this square part. Okay, it's here. So we eliminate R, then we remain with the RQ over R squared E naught times 2 pi RL. So remember from there, so this is just RQ over 2 pi E naught R squared L. So from that point, we need to express this in terms of rho, where our rho, this one is Q over pi r squared L. So this rho is big Q over pi r squared L. So it's already there in this expression. So we have Q over pi r squared L multiplied by r over 2 E naught. So that's Q over pi r squared and L with r over 2 E naught. Everything is scattered for there. Then this part, the first part of this expression is the rho, and the second part remains there as r over 2 E naught. That's quite simple. So I was so worried why all these steps were not adding up to the correct thing, but the steps were correct. It was only that error with the calculations. So that's something you should also avoid. You might follow the concepts properly, but if you don't do proper substitution, then that's actually very detrimental, very dangerous. So our answer there is rho r over 2 E naught, which is B. Now we are happy. Now we're happy. So it was a pleasure having you around, guys. I hope you were able to follow, and I hope you learned something additional to what you already knew from your lectures. And thank you for your time. Thank you, Hlaluko, for the participation, as well as Tabiso and everyone else. So you guys enjoy your small holiday, but don't forget to keep studying. Keep studying. If there's anything even from the chapters that are already from the previous chapters, you can bring them over when you are here online. We'll be happy and very ready to assist you. Otherwise, all the best with your studies, and have a great weekend. Bye-bye.